Hi, this is Dr. Rich, and I want to go over cell volume that I expect you to be able to do in class. These can be tricky. I posted a document, a Word document called Cell Volume that is really helpful. That document was written by Chris Clausen. He was my PhD thesis advisor, and he's a really smart guy. What he does in that document is explain to you how water and salts cross biological membranes. That's a central concept in physiology and in neurophysiology specifically. So we cover it extensively in this class. When we consider cell volume, there really are 5 rules. And if you use this flow chart, it's really a process, and it enables us to solve any cell volume problem. So I want to go over these 5 rules, and with practice, I think going through these steps will just come naturally. The other thing I want you to know is I've set up all the problems with an A, B, C, D, E, and those problems really follow this format. If you don't understand it at first, bear with me. My hope is that if you don't understand it at first, or if you understand only part of it, that it will get easier as you practice and as you use these rules. So first, always know that the bath solution for these problems that we do is infinite. So a cell is really tiny. It's like a nanoliter or a picoliter. That's 10 to the minus 9 or 10 to the minus 12 liters, which is really small. And these problems are as if we put one cell into a liter, for example. So if potassium leaks out of that cell or sodium, it will not affect the concentration in the bath. Certainly the bath ions or molecules can diffuse into the cell if the membrane is permeable, but that comes later. So just know the bath volume is always infinite. The second thing you do is you calculate the initial osmolarity of the cell and of the bath. Don't think about water moving, just add up the solute concentrations. Now, depending upon those solute concentrations, we're up to number 3, you decide, does that cell swell or does it shrink? If the cell osmolarity is higher than the bath, water is going to go into that cell and it will swell. If the bath osmolarity is higher, then water will move from the cell to the bath and the cell will shrink. So that's the first thing. We do this because water diffuses almost instantaneously. So what we're doing here is we're dividing the problem up into manageable steps, and we're thinking like each step happens one after another. In reality, of course, everything is going on. But to conceptualize cell volume, we separate and conquer. Okay, so we've determined the osmolarity on both sides of the cell. We know initially, will that cell stay the same, swell, or shrink? The next thing we do is we look at the movement of solute. So sodium, for example, we figure out if it can cross the membrane. The first thing that's really important is permeability. So if the cell is permeable to sodium, and the bath sodium is high, it will diffuse into the cell, but not so fast. Sodium's charged, and we know we can never violate electroneutrality. So sodium can go into that cell if the cell membrane is permeable to sodium and if electroneutrality is not violated. Sodium can go in if an anion, chloride, can go with it. That's one possibility. The other possibility is that sodium can go in if the membrane is also permeable to another cation, like potassium. So sodium can go in if potassium can go out. Now notice there's no net charge transfer and electroneutrality is never violated. So we figure out what solutes can cross the membrane, and we figure out what's the final concentration of those solutes. Okay, now we can determine cell volume. All we need to do at this point, that we've determined the equilibrium concentration of all of the ions, as well as the impermeable solutes that are inside the cell, we add them up on both sides of the membrane. If it's more on the inside than the outside, then we know that cell is going to swell. In that case, the solution is hypotonic. If there's more on the outside than the inside, we know that that cell will shrink. Now we can determine if that solution is hypertonic. So you can see we go through these steps, and there we go. And by the way, under equilibrium conditions, the way we determine if cells swell or shrink, it really depends upon the impermeance. And you'll see that in a minute. So here we are on our first cell volume problem. I'm going to try to draw on here. So here we go. The bath solution is 150 millimolar sodium chloride. And we know that adds up to 300 milliosmolar. Now the inside is also 300. Okay, that means it's isoosmotic. And initially, it's going to remain the same. Now let's figure out, I don't have the table on here, but let's figure out what happens at equilibrium. We know at equilibrium we've got 150 sodium and 150 chloride on the outside at all times. Now since sodium is only 10 millimolar on the inside, we know that sodium wants to diffuse into that cell. That can only happen if it can move in with chloride. And in this case, the cell is, let me hold on a minute and look at the original problem. I'm not sure what's it says right here, right? It's sodium is permeable and chloride is permeable. So certainly sodium and chloride can diffuse in, and at equilibrium we're going to have 150 millimolar sodium and 150 millimolar chloride. Notice electroneutrality was never violated. We've also got potassium in the cell, that can't get out, and protein in the cell, that can't get out. So in that case, if we add up the osmolarity at equilibrium inside and outside, we've got 140 plus 150 plus 150 plus 140, which is quite high, right? That is, I believe, 580 milliosmolar. So what that means is at equilibrium, that cell is going to swell, correct? Because water is going to diffuse in. If that cell swells, that means the solution must be hypotonic. I'm going to take a break here and come back on the next slide. Okay, I'm back. So here's the next problem, and the cell is permeable to sodium and chloride, but the bath solution has changed. We've got 280 millimolar sucrose, and that's impermeant. So the first thing is the solution hypo, iso, or hyperosmotic. Clearly the osmolarity of the bath is higher than the cell, so it's hyperosmotic. Now we want to know, will the cell swell, shrink, or remain the same? Well, most certainly the cell will shrink, right? Because the bath solution has a higher osmolarity. Another way to look at this is the bath solution has a lower water concentration. That sucrose is taking up space that would normally be taken up by water, which means water will come out of the cell trying to dilute that bath solution. Oh, hang on, I'm sorry. Okay, sorry for that interruption. So of course the cell is going to shrink initially. Now under equilibrium, what will happen? Let's think about solute movement. What we know is at equilibrium sodium is going to move in, and let's think about electroneutrality. Chloride can move with it. So we're going to go up to 150 millimolar sodium and 150 millimolar chloride, correct? So once that sodium chloride goes up to 150 millimolar, the internal osmolarity will go from 300 milliosmolar up to 580 milliosmolar, right? Because it's 140 plus 150 plus 150 plus 140. So we've got 580 on the inside, and we've got, what do we have on the outside? 580. Ah, interesting. So that's the equilibrium solute concentrations, and it's balanced on the inside and the outside of the membrane. So that means that cell is going to remain the same volume, which means that the solution is isotonic. So I hope now we've done two problems. And what you're seeing is the first thing you do is calculate the osmolarity at the starting conditions of the bath and the cell. Then you can tell if under initial conditions is that cell going to change volume. The next thing you do is you think about solute, just solute. You say, how does the solute move? And you think about membrane permeability, and you think about electroneutrality. Now, once you've figured out the intracellular and the extracellular solute concentrations at equilibrium, that means after a long time, then you think about cell volume at equilibrium. Now, once you know that cell volume at equilibrium compared to the initial condition, right? Compared to the time when no water moved, right? The initial condition. Now you know if that solution makes cells swell, i.e., is it hypotonic, or does it make cells shrink, i.e., is it hypertonic? I hope I said that right. Or if the solution doesn't make the cell change volume at all from the initial conditions, that would be isotonic. So now let's look at this last problem. Now the bath is 300 milliosmolar, right? Still 150 millimolar sodium chloride. And the cell is 300 milliosmolar. That means it's isoosmotic, and that means it will remain the same, initial conditions. What's the solute going to do? Well, in this case, potassium can leave the cell, and so can sodium, or sodium can enter. So we've got a situation where only cations are moving, but for every potassium that leaves, a sodium can enter the cell. They can exchange. So electroneutrality is not violated. So I think what's going to happen is intracellular potassium is going to drop to 0. And sodium is going to increase to 150 millimolar. Chloride is going to, chloride can't go in. But what we know is that chloride is going to be, if it stays at 10 millimolar, and we've got 140 millimolar negatively charged protein, we're in good shape, because then electroneutrality has not been violated. So if we have 150 sodium, and we've got 150 anions, that means the intracellular osmolarity is going to be 300 milliosmolar. So that cell is going to remain the same volume at equilibrium, and therefore these solutions are isotonic. So there you go. That's done. If you need to, do these problems several times yourself. I think that this is difficult, and we'll do more next week. Ultimately, I want you to be able to tell me what's the time course of these changes and draw a graph of cell volume versus time. So we're going to have time, and here's going to be cell volume, and right there is going to be the initial condition. So we'll see how that goes next week. Good luck, everybody, and I hope this is helpful. Bye-bye.